Good afternoon, everyone. So it's my distinct pleasure and honor to reintroduce Dr. Avadh Saxena, who's visiting from Los Alamos National Lab. Uh, Avadh is a very distinguished researcher. He's worked on, actually, maybe we need to count what he hasn't worked on. So he's contributed to martensitic transitions, then liquid crystals, so hard and soft matter. He's looked at the electrical, optical, magnetic, maybe twist, bends, play as well properties of hard and soft matter. He's recently authored a book, co-authored or authored?
Co-authored with
Co-authored a book on phase transitions in materials. He is a fellow at the lab. He's a fellow of the American Physical Society, and he has too many visiting and adjunct positions to list here. So, and today he is giving us a talk with a more pedagogical flavor or more of a broad review on topological defects in condensed matter, but it covers both hard and soft condensed matter. So, without further ado, let's invite Dr. Saxena. Thank you.
So, good afternoon. Mahesh, thank you very much for a very kind introduction. And I want to thank Mahesh, I want to thank Jonas, TVSP for magnificent hospitality. It's so magnificent that yesterday I had to go to the clinic downstairs because after playing tennis, my left knee was having some pain. And the doctor says, I saw your poster, you're giving a talk, everything is free for you. And please come to OIST again. That's called absolutely magnificent hospitality. So in my last talk, which was more complicated about hopfions, in the introduction, I actually gave a lot of historical backdrop of Los Alamos, the Manhattan Project, how things happen. Today, I have so much stuff in this one, I'm not going to dwell on history or other stuff at Los Alamos. I want to give you a pedagogical, more didactic, at the same time discursive aspects of topological defects in both soft and hard condensed matter. So when we didn't have phones, we didn't use the term landline. When you didn't live on an island, you didn't use the term mainland. So if you don't know topological, if you know topological, then you ask what is non-topological. So I hope this will become clear to you. What are non-topological defects? Things like point defects, interstitial stuff like that, domain walls, solitons, skyrmions, hopfions, and a whole zoo of other interesting objects are topological defects. And I'll make clear what I mean by that. And then I'll give some examples, interchangeably between soft matter and hard matter, liquid crystals, vesicles, polymers, colloids, crystals, newly emerging topological materials like Dirac and Weyl semimetal, topological insulators, topological superconductors. So this has become very interesting. Of course, there's a traditional way of thinking about nonlinearity in dispersion. And that leads to soliton-like equations, phi-4, sine-Gordon, nonlinear Schrodinger, whatever. I will see how much time I have and how much I can illustrate, but I do want to dwell on monopoles or emergent monopoles and condensed matter. I want to make one more point before I go. Anything you see in any field, let's say in soft matter, hard matter, magnetism, you also see in other fields, photonics, hydrodynamics, plasmonics, cosmology. So many of these ideas are much more ubiquitous than you will see here. I always like to start either with history or philosophy. Today we'll start with philosophy. This is a crystal clear universe, and we keep exploring with the Webb telescope and whatnot. And there's the idea of reductionism. You start from universe all the way down to quarks and high energy physics. So Wolfgang Pauli, by the way, the solid state physics actually started in 1949 from Cornell. Jim Krumhansel taught the first course. And it took some years until 1978 when American Institute of Physics renamed it condensed matter physics. But many of the people who believed in reductionism, which is actually very nice, called solid state physics as quality state physics, physics of dirt. It's every time you do an experiment, you get something different, particularly in semiconductors. They didn't like that. On the other hand, Phil Anderson, wrote a very nice article in Science in the 70s. More is different. It's about all kinds of phenomena that you study when you have many body interactions of particles, be it fermions, whatever, superconductivity, superfluidity, many different kind of, let's say, topological insulators. They're emergent. You cannot go down this path. That means every crystal itself is a universe. You take a crystal of some kind, it is a symmetry, you put some orbitals, you put some electrons, and the interplay of spin charge lattice leads to incredible variety of phenomena. So that's emergence or emergentism. Anyway, so I think my talk will be on this side. Now, what's topology? I mean, I think most of you know topology, but if you take an object and continuously deform it without any 2-point touching from far apart or cutting. So you see, you can continuously deform a coffee mug into a donut because coffee mug had a handle. That handle means the hole remains intact. So it preserves, continuous deformations preserve some invariant property. In this case, it happens to be the handle or genus, the number of holes. On the different, if I go to differential geometry, there are only 3 minimal surfaces. Minimal surfaces means the mean curvature. So at every point on the manifold, you have 2 curvatures. You have mean curvature, which is the average, and Gaussian curvature. So if the mean curvature is 0 at every point, like in a plane, but that's a trivial, nothing interesting. There are only 2 surfaces which are minimal, which means at every point, if the mean curvature is 0, kappa 1 plus kappa 2 is 0, that means kappa 1 times kappa 2 has to be negative at all places. That means constant negative Gaussian curvature. These are catenoid and helicoid. You see, so this is helicoid, and you can continuously deform into a catenoid. These are topological equivalent because I'm continuously deforming without doing anything. So 2 minimal surfaces, 2 non-trivial minimal surfaces can be continuously deformed into each other. You can look at it in another way. So I just said topology is an abstract concept in mathematics, studies invariance of certain properties. Here I just talked about genus, but there are a whole slew of other invariant properties. That one can study, as you see later in my talk. And the point is about under continuous deformation. And it can also be used to describe different objects. For instance, I just said the orange is not the same as donut. A donut is not the same as the pretzel. Genus 0, 1, 2, 0 hole, 1 hole, 2 holes. Here is the connection between geometry and topology. G is the genus, chi is the Euler characteristic. So there is a connection somewhere. Topology and geometry. So if I take a manifold, continuously deform it, this part remains invariant. So high energy physicists and many other branches of physics and mathematics have used topology a great deal. Only last decade and a half, topology has becoming mainstream in condensed matter physics, and that's what I want to touch upon. Now, in 2016, the Nobel Prize was given to Mike Kostelis, David Taules, and Duncan Haldane. And this is the picture from direct Nobel lecture there. So the same thing I showed you in the previous. Here's the ball. It's like a cup without a handle. Here's my bagel, cup with one handle. Nobel Prize was given in Sweden, in Stockholm. So it's so 2 pi times chi is what is written here. It's a Swedish pretzel, which is like a love cup. And here's a German pretzel with 3. I'll let you imagine what this cup means. All right, so one more. And this is an article I actually wrote a long time ago, a decade ago, for material scientists, because I tried to do a symposium topology in materials at MRS. They said it's all mathematics, completely useless. So I said, give me a chance. I got 2 Nobelists to explain everybody. And they said, oh, please write an article. We want everything's topology in materials. Anyway, I had to explain what this was. If you take a rubber band, you can put it on a hexagon, you can put it on anything. It's the same thing. You can also twist it, as long as you don't touch it. The moment you touch it, changes the topology. You're not supposed to do that, okay? So anyway, so if you are in the nanocarbon, here's a buckyball. In nanotube with both sides capped, they are topologically equivalent. Forget about the atoms, just continuously you can deform them. But they are nanotubes without a cap, They are not equivalent, things of that sort. Okay. All right. I have a completely different talk about art and architecture and topology. And incredible buildings around the world, the latest in Dubai with beautiful topology, but this is the one in Guangzhou. They're buildings with different genus in topology and beautiful architecture, but I'm not going to develop on that. So let me get to some science. Let's start with an example in biology. So you can have vesicles with many, many holes. So genus, high genus. You can also have synthetic vesicles up to 50 genus or things of that nature. Here on this side, you have many different genus, vesicles. They all have 5 holes or something. So if I want to ask a question, if I deform this, think of this as a manifold deform. What is the elastic energy of deformation as a function of genus, number of holes? Let's suppose I want to do that. How do I approach that problem? Helfrich thought about that a while ago. So I said when I was talking about the surfaces, minimal surfaces, catenoid and helicoid, they had a mean curvature and a Gaussian curvature. This is kappa 1 plus kappa 2 by 2. This is kappa 1 times kappa 2. So there's a bending rigidity kappa 1, and there's a Gaussian rigidity kappa 2. So you can write a free energy for a closed manifold, even open, but bending, and that's the elastic energy. But if you have vesicles, biological system, you have other constraint. That means the area may be preserved. So you can put some Lagrange multiplier here and say, okay, I will minimize this free energy with this constraint. You might have osmotic pressure. So you couple it with volume and you minimize that. I'm not going to do this analysis explicitly, but if you were to calculate this analytically, it's very difficult. You have to do numerics. Anyway, so you write an Euler-Lagrange equation, second order differential equation, difficult to solve. But there's a trick in topology called Bogomolny decomposition, that the energy, whatever you have, is greater than 4 pi times some topological invariant. Let's call it topological charge, could be winding number, etc. So if you take the second order equations, you can actually split them into 2 first order equations under some constraint. When they are exactly splittable, then you say you have the Bogomolny bound meshed equal. If you do that, then you can actually, I'm not going to show you the details, you can look it up in this paper. So here, well, this is called elastic energy. The technical term is lost in sequence, doesn't matter. So this is sphere, this is torus, vesicle 2, 3, 4, genus, etc. Using that Bogomolny bound, that means taking the second order differential equation, bringing them to first order, and using the topology. You can calculate this exactly, but higher ones. We use what is called Brake's surface evolver, and we could calculate the energy. And so this is numerically done, the pluses, the radius from my Bogomolny bound, the topology, and it's approaching. But in doing so, okay, if I do 1 over the genus and the elastic energy, I get some kind of scaling. That is not so important. But I was just trying to understand what we kind of numerically proved a conjecture in pure mathematics, that if you have infinite many holes, it reaches a bound, which is 8 pi. This in mathematics is known as Willmore-Choosner conjecture, which has never been proved, but here is a numerical proof. Anyway, this is a side remark, but it was quite gratifying. There are certain viruses. This is a very nice paper from David Nelson. And so there are certain viruses which have this kind of topography. And they have a lot of, I'm not showing all the details, many disclinations, 5-fold disclinations. So if you take a triangular net and create a disclination, it will bend curve like this. And by doing this and using the Helfrich free energy that I showed you in the previous, they were able to do some MD simulations and also look at where these bulgings happen and what kind of disclinations happen in this. I'm just giving you an example, and this is one Kalman number. So if you're looking at your calculation versus actual observation, for what von Kalman number you'll get the optimal structure, etc. Just to give an example. Another example, again, without going to details, you take 2 different kind of copolymers, mix them, A-rich and B-rich, and here is the number of monomers times some polymer-dependent quantity, and you get this beautiful zoology of structures from lamellar to face-centered cubic to hexagonal, close back to bicontinuous gyroid, double gyroids, last space group number 230. And again, using some topology and some kind of field theory, you can actually reproduce this phase diagram beautifully. This is a nice article to read about it. I'm not going to go much into detail, just to give vignettes of what is possible. By the way, please stop me if you think something you're not understanding or not making sense. Now, let me spend a few minutes on hardcore material science. You know, material scientists think of materials bonding and crystal structure plus defects. You can derive all the material properties. Sir Frederick Charles Frank said crystals or materials are like people. It is the defects that makes them interesting. You know, who likes boring people, right? So you think of, you know, zero-dimensional defects like vacancies, interstitial impurities, one dimension, like edge dislocation in 2D, disclinations. In 2D, you have grain boundaries, you have twin boundaries, stuff like that. In 3D, you can have hetero phase inclusions, hopfions, whatnot. So just quickly, I'll show you some pictures, then we'll come back to some real science again. So if you don't know, in material science, you have some crystal with some orientation. You can have another crystallite with different orientation, but they all, in fact, real materials are like this. You never hardly get a single. So these are called grain boundaries. They can be low angle, high angle. The strength, ductility, brittleness, a lot of properties are determined by these. It's a very, very important problem in material science, including your aerospace engine. You have titanium alloys, and depending on what's happening, whether the engine cracks or doesn't crack, whether it's ductile, all kinds of things. Okay, so if you have some material that's a square and it's undergoing square that is undergoing some phase transition to rectangle, you have two kinds of orientation. Both of them are equi-energetics. They must coexist. But how should they coexist? They coexist such that the elastic energy is minimized, so you need a mirror plane. So that's why it's called twin boundary. And similarly, you have other kind of grain boundaries and whatnot. So when I say topological, what do I mean by? When I say topological defect, what is topological? What is not topological? So let's understand a simple example. Everybody knows the double well potential. So suppose I write some free energy with some order parameter, could be applicable anywhere. Actually, it's a model for second order phase transition. So you have a double well potential like this. And if you have the domain wall or something in between or inhomogeneity, then you take the gradient of order parameter times some cost of creating a domain wall. So here you see you have two minima. You write the corresponding Euler-Lagrange equation, integrate it twice, you get this kind of equation. So you put this potential, you can invert, you get this solution for double well. What it is telling you is that, as I said, suppose I had a square lattice, you can have rectangle horizontal here, rectangle vertical here. So they would be, they are equi-energetic. So you interpolate from here to here. That means the solution looks like this. This is the simplest soliton or domain wall. It's topological. Why it is topological? Because it doesn't stay in one well. It goes and samples other well and comes back. Or in this case, doesn't come back, but it could come back. So it starts from here, goes here, comes here. And phi is a function of x. I'll show you in a moment. So this is your double well, v of phi and phi of x. So you start with minus infinity from here, go over the barrier. That means started from one minimum and now end up in another. This is topological because each minimum in mathematical sense belongs to a different homotopy class, a different topology. So things interpolating between different minima, different homotopy, different whatever you want to call is topological. And you would also have domain wall lattice, but now what is non-topological? Suppose I start here somewhere and I try to go up and come back. I cannot go over the barrier. So then I'll get hump-like structure. That's a non-topological domain, non-topological stuff. Okay? So let's look at some pictures, then I'll come back to some interesting stuff. So dislocations. So missing planes, missing lines, like here in this maze, or you can have dislocations. So these are topological defects in materials. It's very important for the strength of material. Suppose you have crack propagation. If you look at the end of crack, do some kind of interesting MD. At the crack tip, you have proliferation of this entangled dislocations, and that tells you how strong or brittle, etc., the material is. So this is a very important problem in material science. And of course, in magnetism, you have domain walls, vortices. It's very important for the magnetic storage memory you have in your computers. Similarly, you have materials in which polarization and magnetization couple. It's called magnetoelectrics, or more generally multiferroics, and you can get very interesting kind of these experiments. Vortices and topological defects. And finally, here you have some kind of dislocation. Basically, you cut out something, join it, you get disclination. I will say a few words about solitons, and then I'll come to skyrmions. Just very, very basically. I mean, there are some experts in the audience who know solitons very well, but 1834, this gentleman near Edinburgh, John Scott Russell, saw a wave on the ocean, which was like a bump, and it maintained its shape. And he couldn't believe he chased it on a horseback for 5 kilometers. And he said that was the most amazing thing he ever studied. And he wrote that 10 years later, a report on waves. So he had a T-shirt and whatnot with this. It took 61 years for mathematicians. This is Dutch mathematician Korteweg and de Vries, which figured out the shallow water waves, this third order differential equation, and it has all kinds of beautiful properties. And then Zabulski and Kruskal in 1965 were doing some simulations. From simulation, they saw similar kind of structures, and they called it soliton, a solitary wave. So solitons are much more general topics. This is the famous breaking wave, great wave of Kanazawa. This is at the coast of Oregon. This is tsunami. So in hydrodynamic systems, these are very, very popular. But the idea of soliton or domain walls, whatever is, you have a balance between dispersion and nonlinearity. If I touch water, as soon as I touch water, the bump decomposes itself into Fourier. That means you get ripples. If I put my finger on honey or molasses, it doesn't, because it's not, it's highly nonlinear. I mean, it doesn't have dispersion of that kind. And nonlinearity means how viscous. So when the conditions are such that, I mean, the shallow water, that dispersion is completely balanced by nonlinearity, you get just soliton-like solutions, domain walls, etc. And they can go through each other just like particles. So this is very interesting. Okay, next many minutes I'm going to spend on non-collinear topological defects called skyrmions. So, as I said in my last lecture, Tony Skyrmy was a graduate student, 22-year-old at Los Alamos, worked with Rudy Piles. After he left, he went to Birmingham, England, and he came up with the topological soliton model for understanding nucleons, actually in the context of quantum chromodynamics. That didn't become so useful. But the idea of skyrmions actually became much more useful in material science much later, and that's what I'm going to look at. So I mentioned this last time, but let's look at this one. So this is some vector field configuration. In this case, magnetic spins doesn't matter. The spin is down here, and as you go out, you have all the spins going up. So this is called Nail's skyrmion. If I cut it this way, it's a cycloid. So you remain in the plane. And there are materials like gallium, vanadium sulfide, which actually harbor Nail's skyrmions. Now you can comb it, you get this skyrmion, which is topologically equivalent, and this is called block. A skyrmion is manganese silicide materials. Now, if I cut it this way, the domain wall is helical. So this is called block domain wall, okay? So that was seen already in 2009, but people were looking for, can I get anti-skyrmions? It took 8 years, manganese, platinum, palladium, tin, they had to figure out, and they were able to experimentally observe anti-skyrmion. So what's an anti, like vortex, anti-vortex, but what is here? So I said, if you cut it here, this is block skyrmion, this is Nail skyrmion. If you cut it here, you get this helical domain wall. If you cut it here, you get cycloidal. If you do Lorentz transmission electron microscopy, LTEM, on this material, for chirality here, you will see this blob. If you do, because there's no chirality here, there's no combing here, you see nothing. This is a combination in between somewhere. Anti-skyrmions in between somewhere. So the green arrows are the magnetization, red arrows are in the Lorentz TEM, electron diffraction, deflection. So you get this, you get very different, and you get a combination. So if I cut it one way, it looks like block skyrmion. If I cut another way, it looks like nail skyrmion. So a little bit of material science, what kind of material? This is manganese silicide. You don't have to know the crystal structure. The only thing you need to know that this crystal structure lacks centrosymmetry. That means if I put a mirror plane, I cannot overlap them. This is very important because breaking, especially inversion symmetry, leads to some properties which will become clear in a moment, this handedness, okay? This basically means you have what is known as Zhelezhinsky-Moria interaction, DMI, in the magnetic system. So Zhelezhinsky, I knew Igor Zhelezhinsky was a student of David Landau, and he wrote this paper way back just phenomenologically in the spirit of Landau, that you have symmetric interaction in spin Si dot Sj, but there must be an antisymmetric interaction Si cross Sj. So he wrote that phenomenologically, but a year later, 2 years later, Toru Moria in Tokyo actually showed that that was nothing but underlying spin orbit interaction. In other words, this is your usual symmetric exchange in magnetic system, Si dot Sj. This is Si cross Sj. But if you want to make energy as a scalar, you need a vector. So let me explain what that means. That means, suppose you have two spins sitting on two iron atoms, and it's mediated through oxygen. So this oxygen can move like this, okay? So the interaction between these two iron spins is mediated by some other ion, which, so X times Ri gives me some kind of vector. Ri cross X gives me some effective vector coming out. This is the Zhelezhinsky-Moria interaction. Basically, it's phenomenologically the underlying spin orbit coupling. Well, it's very useful in material science. It leads to non-collinear vector fields. That's what you saw in skyrmions. And if you have an antiferromagnet, no Zhelezhinsky-Moria interaction, that means they're collinear. They are tented antiferromagnets. Antiferromagnets should not have any magnetization, but they do find an experiment residual magnetization. That's a consequence of Zhelezhinsky-Moria interaction. So this was the first observation in Munich in 2009 of magnetic field versus temperature for small angle neutron scattering. And they saw helical arrangement of spins. If you increase magnetic field, you see conical, and then it becomes field polarized. And here it's paramagnetic. There was a small pocket here, which until 2009, because we didn't have the resolution, they thought was what were known as magnetic bubbles. But finally, they could see that this was nothing but the triangular lattice of skyrmion. This is the first observation of skyrmion in materials. Of course, you see the telltale six-fold signature in small angle neutron scattering. So you can quickly make a simple model. That's what so you have the usual, I wrote it in a different language, but N is the S. So gradient of spin square. So Si dot Sj, if you write in continuum fashion, this is a gradient of spin vector squared. This is the Zeeman term, means a spin interacting with external magnetic field. And this is the Zhelezhinsky-Moria interaction. The antisymmetric Si cross Sj could be written like this. And these materials have magnetic anisotropy, so I'm going to put this term, okay? Now, I have to show you this because it builds the whole infrastructure on which to understand a lot of topological things in a moment. So suppose I look at the simple phase diagram of this thing. I change D over J in some fashion. So you get the spiral phase as you saw in the previous diagram. And then at a large magnetic fields, you see ferromagnetism. In between, you do see a lattice of skyrmions, triangular lattice of skyrmions. So the simple model, the nonlinear sigma model or gradient of, okay, let's call it symmetric exchange, antisymmetric exchange, Zeeman, and anisotropy. Now let's ask the following question. I want to change this, have everything as it is, and change the anisotropy. And what happens? So on the left column, I have the spin structure. Actually, And the blue and red means the Z component of spin. In plane spin texture, you can see, I think can you see from the back, any spin texture? And this is the corresponding topological charge density of what is happening. And I'm going to increase systematically anisotropy in that Hamiltonian. So you see here, you see a triangular lattice of skyrmions, and each skyrmion covers a unit sphere once. It is winding number 1. As I go down, these skyrmions start pushing each other, and you start creating some vortices between 3 spins, okay? And then it undergoes the first order phase transition, and you get square lattice of skyrmions, and in between there's a vortex here. This vortex will soon become a meron. So here what you're noticing is that these textures that are evolving, this here, it was completely covered sphere. Let's call it skyrmion, anti-skyrmion. So this is partially covered, this is partially covered. So you're fractionalizing, you're breaking a skyrmion until it becomes a square lattice first order transition. Let's do one more thing. Let's actually increase the anisotropy even more. Even more interesting thing happens. So now what you get these blue dots, if you can see, are half skyrmions, merons, called merons, and red dots are antimerons. So you get filaments of these merons, each containing an antimeron. And this is very interesting. If you want to see it in a much more how this spin field is doing. So again, blue and red are color for the Z component of spin. And so here is a meron. It only covers, so spin starts like this, and it becomes horizontal. That's it. So it covers this sphere only half time. It doesn't go fully. So the blue things are merons, and this is the opposite vorticity or helicity, whatever you want to call antimeron. And these things are very important. Now, when we wrote this paper, we submitted to TRL, and we said these were metastable states. And the referee says this can never be observed. So it cannot be PRL. 2 years later, here in Tokyo, Tokura-san, beautiful. They said they saw our paper, and they were, okay, I cannot create, but they were able to create some material, magnetic material called cobalt, zinc, manganese, something, in which they exactly saw meron lattices, etc., as predicted in that paper. So based on my decades of dealing with interesting reviewers, half my papers were initially rejected, okay? In 15-20% of the cases, they said this will never be seen. I don't know how they know it. But I should say that 1/4 of the review was so good that they understood more than I did and gave me new ideas. So it's a mixed bag, but here's an example. 2 years later, they immediately said, look, we found it with the right boundary condition. Even if something is metastable, you can make it stable under right conditions. So there was that, okay? Now, as I said in the beginning, if some phenomenon happens in one vector field or one context, in this case, magnetism should appear elsewhere. Last time I mentioned it, you can see skyrmions and hopfions and photonics and plasmonics. In water, this is a recent paper. So you create, this also in Japan, actually, in Riken. So you take a tank, create standing wave with the right kind of 120-degree standing wave, and you create skyrmion-like structures. And this is a nice paper, and it tells you how to create skyrmion lattices, meron lattices, whatever. And of course, in optics, they are beautiful skyrmions. They have applications for imaging topology of materials. I cannot go into all that, but this is beautiful. And this is just like, and you can move those. It's just like you can move, what happened here? I don't see this here. Oh, here it is. So this is actually a magnetic skyrmion, triangular skyrmion lattice, and I'm passing current and how it moves. This is exactly one should be doing for water skyrmions, but why am I showing you this? Because this is very interesting. So when in my Hamiltonian or free energy, you can only do simulation with so much. But if you were able to capture the skyrmion interaction in some way, you could do very large simulation and learn a lot more. So we did that here. So basically, the corresponding equation of motion for my Hamiltonian could be reduced to something very simple: a damping, a Magnus force, and this is what I want to spend for 5 minutes on. It's very interesting here. Z cross V is the velocity, Z is some coordinate, and then you have this effective skyrmion interaction. They may be moving on some substrate which has some pinning force and external drive like current, and see what happens. But before I do that, let me explain this to you. This is very interesting. Let me go back to 16th century when was Newton born? 1642, yeah. So late 17th century, Newton used to go and watch people playing lawn tennis. That's what they call in England. Tennis was called lawn tennis because it was played in grass and with wooden rackets. And Newton always wondered that somebody hit the shot from 6 inches off the ground. How come it crosses the net over and goes down? And he already knew that this is Magnus force. I mean, he didn't call it Magnus force, but he knew what it is. But he never wrote down an equation until much later. I think 1852, Magnus wrote down, if you have a spinning body, which means this rotation frequency times its moving velocity, you get a lateral force, Magnus force. Now, this was technologically very important in Europe because you had some shallow seas, and sometimes they had to lift a ship. So they put rotating spheres down there, and V cross omega will give you uplift. So this was used. Now, I'm sure this is an old picture. Don't read the French here. This is Roberto Carlos, who played with the Real Madrid, and this is a match against the French. And he's taking this kick, and it's exactly with the shoe you give omega, and V cross omega, it lands here, okay? This is exactly, so that's what the football is doing. Skyrmion, when you create a single skyrmion, it's spinning like this, very free object, unless you have strong pinning. And so this has very strong Magnus force, unlike vortices. Vortices, and I'll show you the consequence. But before that, let me actually illustrate. So this is a very interesting place, Gordon Dam in Tasmania. So it's quite deep. I'm going to drop a basketball without spinning. V equal to 0 Magnus force, go straight down. Then I will put a little bit of spin. It will go 80 meters laterally. Now, one video is not working properly, but I hope this one is working. So first I'll drop it. What is the, yeah. So this is 0 spin. So it goes all the way. Oh, no, this is, oh, sorry. So this is with the spin. This is with the spin. And this is with 0 spin. Let me show you the 0 spin one first. Okay, sorry. Let me see. This is no spin. First, let me show you no spin. What is it? Somehow it's not showing up here. Okay, let me just play one. I mean, so this is 0 spin, and that's with spin. It goes laterally 80 meters. This is a beautiful illustration of Magnus. I had a video with sound and everything, but it's not working right now for some reason. But you got the picture? How important is Magnus force? Just with a little bit of spin, it goes a couple of 100 meters down, but it goes laterally 80 meters. Incredible amount of. So that's what skyrmions do, but that is technologically very important. So let's understand that. Okay, so that's what I just said. If I have some substrate and real materials, you have substrate, you have impurities. So vortices move, skyrmions move. When vortices move, they actually get pinned. Magnetic vortices, generally they get pinned because they have very small Magnus force. They cannot rotate. Whereas skyrmions, because of Magnus force, they can avoid some pinning and go like this. So it has important consequences for dynamics. Let's see if this works. So this is 0 Magnus force, which means these particles, these vortices, that's how they will go. I'm just showing you the difference. And if I had Magnus force like in skyrmions and I were to do dynamics, you see, so V cross F is, so now you think of a collection of vortices, a collection of skyrmions, and how the dynamics plays into how things. And this is, by the way, a lot of applications in spintronics. I cannot go into all that. Talking about dynamics, when let's say when the vortices move on some substrate with the impurities, they get pinned. So click, they move, they have a barrier, you get avalanche, you get avalanches. So velocity of vortices as avalanches, you can blow it up like this. You get avalanches, just like in earthquakes. So this is, they have small Magnus force. If you look at skyrmions, and we did that in this paper. So we put a lot of pinning sites, and from one side we push skyrmions inside and ask as they pass through the pinning sites what kind of you get very interesting avalanches. I'm not going to show you any power density distribution, all those. We have full analysis, everything. So again, Magnus force, vortices versus skyrmions, small Magnus force, large Magnus force has incredible implication on the dynamics and therefore technology. I will not go there. Okay. Next, I want to talk about monopoles. Dirac wrote a paper in 1931 or something. Of course, in electromagnetism, there should be monopoles, but actually there are no monopoles because divergence of B equal to 0. But divergence is equal to charge density. That means you cannot have isolated monopoles. But ever since people have been thinking that monopoles must exist somewhere in nature, the weirdest thing was if you have the theory of multiverse, and if you put 4 universes in a tetrahedral configuration, the interstitial space between those 4 universes could support Dirac monopoles, but I cannot do that experiment. So real monopoles have never been observed, but condensed matter again provides a cradle in which to actually explore monopole-like structures. But even before I do that, if you do the very simple, if you just look at simple expansion for magnetic energy, so you will get m dot s Zeeman. So you have a term here, divergence of H, so that's your monopole or anti-monopole. And then you have a term which couples to curl of H. This is called toroidal moment, that you can have toroidal things. And then there's something which couples to quadrupolar things. So when you do the expansion, you have monopole, you have negative monopole, what I call the toroidal moment, which is R cross S spin toroidal moment. That's actually called Z anapole, but you can have also quadrupolar configuration. The question is, can I create conditions in soft and hard condensed matter to be able to observe monopoles? So let me go back to skyrmions for a moment. So what does monopole actually mean? If I have divergence equal to 0, that means I have a point from which radially outward I have some vector field, in this case electric field. So if I could find a configuration where from a point I have radially outward magnetic field, that's actually like a monopole. So I showed you a skyrmion, and in my last talk, not today, in many crystals, skyrmions come as a tube, okay? As a tube. The tube may be joined. When the tubes can split, so this is one tube, this is another tube. Now, when you talk of a tube and you have a non-collinear spin configuration, that means there's an emergent magnetic flux in there, in the tubes. So the point at which these tubes join, ask what is that emergent magnetic field? That's exactly radially outward looking, radially outward looking. So it is like an emergent pseudo magnetic field monopole, which means divergence of B is some magnetic monopole density. So monopoles can be seen in condensed matter. Okay, here's a simulation, not mine. This is from again Munich. So they actually did a simulation of these skyrmion tubes and start applying magnetic field. So when there's no magnetic field, you have lamellar structures of spins. Then they become joint tubes, and then the tubes separate. So in this region, you have a lot of such structures, and you see monopole, anti-monopole creation. Means points where the emergent magnetic field is radially outward. Okay. So this is one example of monopole observation, but there's a whole field called artificial spin ice. So how should I go back? 1930s again, Linus Pauling. So you have water molecule, H2O. So you have O, you have 2 orbitals, but there are 2 empty orbitals here. So if you calculate the entropy of a water molecule, it is non-zero. and this is because there's frustration of current. So you can create same thing in nano islands of permalloy, in which you can say that I will have two magnetic spins doing this way, going in, two out, and you create configuration in which there's magnetic frustration. So that's called artificial spinice in a very simple language. And then you can create configuration in which at certain vortices you have point-like spherically outward emerging magnetic field. So you have in artificial spini emergent monopoles, and therefore these are called magnetic charge. Electric charge, magnetic charge. So when you have electric charge moving, you have electricity. When you have magnetic charge moving, you have magneticity. There are papers about how to use magneticity for something. And here's an experiment at the Argonne National Lab in which they looked at monopoles in artificial spinice. This is what I was talking about. So you create permalloy nano islands, and you have south pole, north pole, two in, two out, and you can create frustration, and then you create monopole and anti-monopole. Now, monopole cannot be created in isolation. So when you create just like vortices, anti-vortices, your monopole, anti-monopole, they must necessarily be connected by something known as Dirac string. This Dirac string contains pseudomagnetic flux. So there's a lot of research going on. I'm not going to dwell on that. But as I said, if something happens in one field, also happens in another field, how about bosons and condensate? This paper you should look up. I'm not going to dwell on this. Observation of monopoles and bosons and condensates, the way they created in the simulations and rubidium atoms in synthetic magnetic field, but I will leave it there. Okay, so I have less than 10, 15 minutes, so I'll keep going and I'll stop. Mahesh asked me to shut up whenever you want me to shut up. Okay? Okay, I want to go back to liquid crystals for a while. So all that I told you in something about magnetism. But do similar things happen in skyrmions? I mean, in liquid crystal, the skyrmion-like things. So when you have liquid crystals, you have no arrows, unlike magnetic field or electric field. You have no arrows. You're directors, or molecules oriented. So that's called N, director. But if we want to do simulations or understand liquid crystals, sometimes there are disclinations and other similarities. Using director field is not good. It leads to problem. So in liquid crystal context, you use something called Q tensor. And that Q tensor is defined in terms of the components of the director field like this, and S is some scalar order parameter. So now you just like in magnetism, you have some free energy, double well here, you can have trace of, so this is the free energy in terms of Q tensor for the liquid crystal. Here you have magnetic domain walls and chirality, because I talked about Zaleshinsky-Moria interaction, that means there was chirality, and Zeeman field and anisotropy. So here, these two terms are elastic interaction in liquid crystal. So this is just like the gradient square. So this tells you that if you do bending, splay, or twist, it costs you some energy. Here you have minus sign and Q naught. Q naught is some inverse length scale. This tells you that the system will prefer chiral nematic order. Okay, so this is elastic. And you can do the analysis, but I'm not going to go into this given my lack of time. And you could create, chirality versus temperature phase diagram. You can see what kind of phases will appear. But there's a one-to-one correspondence between liquid crystals and magnetism, except you don't have an arrow. But not having an arrow has an implication of what is stable and what is metastable. So in magnetism, skyrmion lattice is stable, Meron lattice is metastable. In liquid crystal, it reverses. You can make use of that, and we have done that. I'm not going to deal with this, and that's what I just said. Let me skip all this. Okay. What I will do, 5 minutes, I'll just flash a few things without explaining anything. And then I have 5 minutes, I want to talk about quantum topological material. So in soft matter, there are other kinds of topological defects. This is called bosoms. It's a tree-like. Bosom is a kind of tree, very interesting object. Oh. Yes, at UCLA.
David Mermin.
Mermin. And then in liquid crystals, you have some very interesting topological called Schlieren topological defects. You have umbilic topological defects. Now here is granular matter. This is dynamical. So you take granular matter and shake it, and you create these oscillating localized things called oscillons. This very sweet. So each thing is in itself is a field I cannot talk about here. And you can mix colloidal particles, liquid crystals, and create all kinds of topological things. I'm going to skip everything. This I'll completely skip because they're experts in the field here. But you can do solitons in sine Gordon, nonlinear pendulum, breather-like structures, and okay, I must spend some time here. Sine Gordon equation has single soliton solution, a breather solution, a soliton lattice solution. It so turns out if you take sine Gordon equation and I can rotate it, which I have done here, this equation has one-to-one correspondence with surfaces of negative Gaussian curvature. There's a beautiful paper in 1994 in which the soliton becomes a pseudosphere in the differential geometry and breathers become more. So there's a connection of nonlinear equations with differential geometry, and each topological defect can be viewed as some non-trivial manifold. Cannot go there. If you have first order phase function, you can do all these triple well things. Let me skip nonlinear Schrodinger equation solutions, the KdV equation, yeah, Boussinesq. So nonlinear Schrodinger equation second order, then you get third order in KdV and fourth order in Boussinesq. Okay, forget about discrete solitons. You can do all this biology. Okay, few minutes, 5 minutes. I want to dwell on this. So a lot of things I talked about so far is topology in classical sense. Condensed matter, you have Brillouin zones, and electrons are doing interesting things. In last decade and a half, this field has exploded because it's beautiful physics. So what happens is it started from, let's say, graphene. Graphene is a two-dimensional monolayer graphite. It's hexagonal lattice. If you look at the band structure, you have bands crossing linearly. Okay, crossing linear dispersion. Typical band structure, you have Schrodinger equation, so you have quadratic dispersion. Here you have linear dispersion, P dot sigma, Pauli matrices. So graphene is a Dirac material because relativistic electrons behaves like relativistic electron. So now there are many more materials which have Dirac cones, which means dispersion is linear at low energy. So these are called Dirac and Weyl semimetals. Why semimetals? Because the point at which it crosses the gap is zero, like in bismuth. Bismuth is zero gap, but the band structure is. So you have double cones which are similar, then you have Dirac material. But you can split those. Let me explain. So anyway, so this is actually in case space in the Brillouin zone. It's a band structure, but you have Dirac cones, linear dispersion. Now, in some materials, which are called Weyl semimetals, these Dirac momentum energy was K. These two Dirac cones can be split, plus and minus Q naught momentum. These are called Weyl nodes. Okay. Weyl node means, so this is very interesting. So now I have split it, and these are Weyl nodes. If you have Weyl, means you are now distinguishing between left moving fermions and right moving fermions. And these fermions now, the spin helicity connects with the electron or fermion momentum. This is incredibly consequences of quantum computing. I'll come to that in a moment. But for simple ways, you can ask in the band structure, if I go from one part of the band to another part, the Chern number changes. I'll tell you in a moment what Chern number means. How do I say some band is trivial or some band is non-trivial? So how to calculate Chern number? Additionally, if you have two Weyl points, that means on the surface there is a Fermi arc. Generally, your Fermi surface means completely connected. Now your pieces, it's called Fermi arcs. And this has incredible consequences for ARPAS, angle resolved photo emission spectroscopy. I'll show you in a moment. Mahesh, can I have 5 extra minutes? Because there's some more interesting. So here is, if you've not read the original paper about Dirac, it's absolute beauty, mathematical beauty, but physics, the elegance. So Dirac wrote, so you had Schrodinger equation 1925, okay? But there was no relativistic. So Schrodinger equation doesn't have fermions moving. So Dirac, so that's why you have 2 by 2 Pauli matrices. Dirac wanted to know what happens to electrons when they're relativistic, because electrons move very fast. And that's the Dirac equation that he wrote in 1928. So he had to spin up and spin down. There are no concept of spin does not exist if you don't have relativity. Okay, so you have spin matrices called Pauli, but if you have Dirac, that means you need two copies. So 2 by 2 matrices become 4 by 4 matrices. So non-relativistic fermions, Pauli, 2 by 2 matrices. Relativistic fermions, spin up, spin down, 4 by 4. What about 3 by 3? Most of you don't know that, but that's in particle physics. Gell-Mann matrices 3 by 3. That's 3 quarks. Yeah, so everything is connected. Anyway, so Dirac came up with this equation, which has linear dispersion. Showed the equation as second order has a quadratic dispersion. And you can have a gap. Gap means mass of a particle. A year later, German mathematician Hermann Weyl said, what happens if I put m equal to 0? And he found the equation. He said, oh, this behaves very differently. There's this spin moment blocking and other properties. Oh, this is a different kind of fermion. Okay, let me give you. There are only 3 kinds of fermions in nature: Dirac, Weyl, and Majorana. So 8 years later, in 1937, he did something else. So Weyl put m equal to 0. Majorana said, how about C dagger equal to C? Means particle, its own particle. Therefore, it has to be neutral. So for many decades, people thought that neutrinos are Majorana, not proven. So let me come to that. So what that means is that this is what I just said, that you split the 2 Dirac cones, you make a Weyl, and these nodes are different. So they have spin momentum locking. That means you can distinguish between left moving fermion to right moving fermion. There's chirality in each node, which is different. And the cones have to come in pairs, because there's a theorem called Nielsen-Niemeyer theorem in 1983 that Dirac cones have to come in pairs. Okay. Now, I tell my postdocs and students sometimes not just to do science. Go take a walk, go to art museums, go to sports. Look at, if something exists in science, it must exist in art and vice versa. This is 1937. The German Swiss artist Paul Klee was making paintings. If you look at these pictures, these are exactly, I didn't bring the experimental picture, exactly the angle result photo emission spectra of Weyl fermions. Okay. So, I mean, how he imagined why he did that, but this is exactly what you observe in ARPAS spectra of Weyl semimetal, and he was very creative. It lined this dot that went for a walk. Anyway, the point being, you have ideas already existing in art. I mean, there are examples of Escher's painting. I think he went to Alhambra in Spain and got all kinds of, yeah. Okay, so this is very interesting. Okay. Anyway, so if you allow me 5 minutes, because this is important, historical. From 1937 to 1980, all physicists and mathematicians believed if you had a phase transition, you must be breaking a symmetry. That's Landau's paradigm. Landau in 1937 paper, first time introduced the notion of order parameter without ever writing an equation, just thoughts. If you read the original paper, there's nothing. It's just thoughts of a creative man. And then other mathematicians in Russia formalize it, group theory and symmetry happen. Then in 1982, you have this amazing experiment, quantum Hall effect. There's no symmetry breaking, and everybody's scratching what's going on. Okay, so in 1982, David Thouless, very famous PRL TKKN, they came up with a topological invariant that there is a topology change, not symmetry change. Okay, and that what he called TKKN invariant is now known as Chern number. I will actually show you how to calculate Chern number. I want to do that. But look, there is completely different paradigm now in hard condensed matter. That Haldane then said, so, okay, what is quantum Hall effect? You have 2-dimensional electron gas interacting. You apply magnetic field, perpendicular. Gallium arsenide, gallium aluminum arsenide. Haldane wanted to know, can I get quantum Hall effect without applying magnetic field? So very interesting idea. So he goes to a honeycomb lattice, and there's flux in the plaquettes in the lattice, and that can give rise to, so that's called anomalous, and there are a whole bunch of beautiful phenomena now, which are happening, including all these Dirac semimetals, magnetic topological insulator, whatnot. So this is the physics. Here's the material science. For each thing, if it exists in nature, in your thoughts in nature, there must be material. So it took like 25 years, nothing happened. Then they found, oh, there's a two-dimensional topological insulator. What is a topological insulator? Topological insulator means it's an insulator in the bulk and metallic on the surface, because some state will cross. The moment it crosses, that means its surface is metallic. And then they found topological weak insulators, Weyl's metal. Now you have all kinds of stuff. It's beautiful. Okay. And it goes on, and I'm not going to go through, but I want to calculate something for you so that you know everything I'm doing. Yeah, Majorana. So, well, okay, let me skip this Majorana for the time being. But so there's a lot of technology based on topology now, serious, okay? And this is the original thing. Let me skip all that. So that's what I just said. 1980, von Klitzing showed. So here's the topology. So when you have magnetic field, you have the cyclotron orbits, but on the edge, you can only have half. And if you're a topological insulator, you have half orbits for both spin up and down. So, and then it has an incredible importance for quantum field theory, because the symmetries that are broken in classical physics, when you quantize, and symmetries that are preserved in classical mechanics are broken in quantum field theory. These are called quantum anomalies. There are no tests of quantum anomalies as such, because I cannot move two galaxies, but I can move two electrons in topological. That's the project I'm working on at the moment, and their experiments is beautiful. But I cannot go. So this is the original thing. This is what Haldane did. And this is what I was talking about, the quantum anomalies. You can teach a child how to understand quantum field theory. If you think of a circle, can you define a single valued increasing functional circle? Not possible, which means left and right moving fermions are different. Can I put a vortex or a torus? No way, which is called parity time anomaly, which means I'm breaking time reversal symmetry. Anyway, and then there were topological insulators, whatever. Yeah, this is what I want to say. So 8 years later, in 1937, Majorana, who disappeared in 1938, the whole story. The man is as elusive as his particle, and it has never been found. But condensed matter provides, again, a different cradle. If I take a strong topological insulator and put a superconductor at the edges, I will have, or even if I take P-wave superconductor on some substrate, a wire, at the end of the wire, I must have half the fermions. Half the fermions like C dagger equal to C. I have Majorana fermions. So now, if I create Majorana fermions, I can move them controllably, moving them braiding. Braiding is topological quantum computing. That means if you can do that, most of the problems in quantum computing, which come from decoherence, means you create a state, it disappears. But these are topologically protected states. And that's, so there are so much going on in terms of observing Majorana fermions. I will not go there. I will not go there. Give me 1 more minute. I want to calculate chart number for you before I stop. Here's an example. This is Shen Chern. I actually met him in late 90s when he was alive. You take a square lattice, remove 1 point from it. Depleted square lattice called Lieb lattice. Why is Lieb lattice important? This is 90 degree. If I start bending it, when it becomes 60 degree, it becomes Kagome lattice. If I put spins on it, Kagome lattice is the maximally frustrated lattice. This is zero frustration, but that's not the reason. Okay, so this is the Brillouin zone. And if I look at the band structure, I have bands here. And if I ask what is the Chern number of these 3 bands, 1, 0, minus, 1, 0, 1, minus. So that means they're phase topological transition between Chern number. This is very important. Now, how do I calculate? This is my, just so that you know, I'm not talking in words, I can actually do it. So this is actually fundamental baryology. How do I know topology? So I take, so in Schrodinger equation, I have wave function, corresponding eigenvalues, and nth band labeled by momentum k. So what you do is Berry connection, which is a very simple thing. Take the electronic band wave function, take its derivative, you get the ith component of Berry connection as for the nth band as a function of k. And then from here, you take a curl, component of a curl. That's called Berry curvature. Take the integral. Oh, sorry, there's no square here. 1 over 2 pi over the Brillouin zone, you integrate. It'll give you a topological invariant. It's an integer that's called Chern number. And this is how you calculate. And I've done it for some Lieb lattice things. And that's how you know whether a band is trivial or topological. And has all kinds of implications. So I can go on, but I have to stop somewhere, so I will stop here. Just within symmetry and topology, whole new field has to be discovered, the materials, the phenomena, and it goes on. This is a new periodic table of symmetry and topology, what you can do. I mean, I compressed a lot of information in 55 minutes, so I mustn't stop. And just, I mean, you're not supposed to understand everything, but the idea is to convey enough excitement in the field and why this is important. And this is what I talked about. Thank you so much for your patience and attention.
Questions? Comments? Let me start. Do you know the movie Dam Busters?
Mm-hmm.
You know this movie Dam Busters?
Dam Busters, I heard it, but I don't know.
So, in the Second World War.
Oh, I had one more view graph for students. You know, don't be disappointed if nobody comes to your poster. This happened to Einstein too.
So, British wanted to explore the German dams along the river. And I think his name was Wallace. He came up with this idea of using the magnet's force to spin the bombs so that they keep jumping.
Keep jumping. I see.
So when you show the magnet's force demonstration, it actually flips over the.
Yes. This is not a poster. This somebody took a picture of him explaining something and just made it as if he was at the poster session. But this is quite creative in itself. Questions, comments, or you didn't understand anything or understood everything? Yes.
Do topological defects have topological invariance?
Yeah, I mean, the simple domain wall of soliton I showed you. If you integrate over, you can write, I mean, you can call it topological charge. That's the right way of saying it. It has topological charge 1. This one, you can have topological charge 2 defects and so on and so forth. Yes. Otherwise, they will not be topological. If I just had a hump like this, which is non-topological, you get 0. I mean, if you integrate that. So, yes. So the words actually have precise mathematical meaning, and that's why I had to show that one view graph. That yes.
So these topological invariants for the materials, what's the transformation that they're invariant across? Like what's what is being deformed, or what's the continuous?
Okay. Good question. So in most of the soft condensed matter, other contexts, when I was talking about real space topology. Okay, real space topology. So number of holes that is preserved. For instance, if I stretch something. In the context of skyrmions and things like vector fields, it's whether they cover a unisphere. That's called winding number. Last lecture, I talked about linking number. You know, things link, how many times they link. That's for hopfions. In K space, in quantum, so you're not in real space because your periodicity, so you have to be in a Brillouin zone. Okay, so in a Brillouin zone, you have a Fermi surface. You know, Fermi surface is the surface up to which electrons fill, and beyond that, no. So in Weyl semimetal, that Fermi surface gets broken up. You have surface Fermi arcs. So there are direct implications of topology. So because that Fermi arc was interpolating between Chern number 0 and 1, I thought somewhere. What was my Fermi arc? Yeah, you see? So, so I'm in K space here. There's a band here. There's another band here. It's Chern number 0, means trivial band. And here's non-trivial, means topological band, Chern number equal to 1. And there is a Fermi arc connecting them. And this can be observed in angle-resolved photo emission experiments, and people have done it. I didn't bring that picture. That experiment looks quite like this. Yes. So yeah, in K space, particularly for hard condensed matter, your crystals, you have translation symmetry. So you have to fold everything in a Brillouin zone. And then K momentum in space is much better way to think about. And all the phenomena that I was talking about for topological quantum materials are in K space.
So those would be continuous deformations of the K space, and this is
yes. I can have any space, whether it's a real space, K space, some parameter space. Most mathematicians work in parameter space, which is beyond me. I mean, which has implications. So if you got nothing from this talk or got something, the point being topology is real, extremely important, not for fundamental science and material science, but it has direct technological implications. Once you understand fundamentals, you can manipulate topology. You can exploit it. And another lesson is if it happens in one field, same thing could exist, whether it's water, magnetism, plasmonic, cosmology, hydrodynamics, whatever. So you have to create the right conditions. Yes.
I have a question about, so in material science, we usually hear that the topological protection, you need more energy to break or to change the system topology.
Okay. Yes, that's very simple. Suppose I take a donut. I continuously deform, but I can actually say so much energy that splits. But I said, if you want to preserve topology, you cannot touch it. We touch 2 points. You cannot cut it, surgery. I mean, it's a technical term in mathematics, surgery. So, but if you apply so much energy that you can break the topology. But we are not in those regimes here. Okay.
So my question is more like, from the point of view of quantum physics,
yeah.
What is the equivalent idea, like besides the topology protection of the state?
Yeah. So, okay, here. You see, most of the physics is near here. It's called low energy. But you're going to do laser excitations where these things go higher, much higher up. Then topology becomes not so important. You destroy it. You have things like higher harmonic generation and other phenomena. But a lot of the condensed matter, interesting physics like magnetotransport or other phenomena happen here, where linear dispersion, which means relativistic physics, is important. Yes. Yeah.
Question about this stabilization of the merons.
Stabilization of meron. Yeah. So meron covers the sphere only half winding number. So in the magnetic systems, if you calculate configuration of a meron versus a skyrmion based on the Hamiltonian, you'll find its energy is slightly higher. Okay. So skyrmion lattice is stable. In contrast, in liquid crystals, the other way around. If you calculate the meron lattice, and this has to do with now not so much the topology, I mean underlying topology, but fields, magnetic fields, electric fields, have arrows. Here you have molecules, only orientation. So it's different physics. But you can always make metastable states stable under right boundary conditions and the condition, because these are mathematically ideal things, but real materials have all kinds of boundaries. So yeah.
So it's a sort of a genuine topological object in liquid crystals, but half an object in magnetic systems.
What I said is the following: skyrmion lattice is stable in magnetic system, meron lattice is metastable. In liquid crystals, at least for the systems we looked at, meron lattice is stable and skyrmion lattice is metastable. That's why the PRL referee told that your thing is metastable will never be observed. But you can create right boundary conditions in experiments. So all these things I talked about are ideal, but real systems, yeah. Yes. There's just one more. Yeah. Yeah, go ahead.
So the plot that you showed.
Which plot?
Free energy versus genus number.
Oh, yeah. In the beginning. In the beginning. Okay. Yeah. Now, where did it go in the beginning somewhere? Yeah. Yes. This is, I'll have to explain how to calculate that if you wanted this one. Yeah.
What is this y-axis?
This is actually elastic energy of deformation. I've used this lambda g because I've used a mathematical term called loss and sequence. The loss and sequence corresponds to genus something elastic energy.
But so does it mean that if you just break the topology, but into the higher genus number, it is more easier to break it? Because
I'm not, I'm not breaking it, but yes, what it's saying is if I take a manifold with infinite many holes, this is the bound, mathematical bound called Wilmore-Klusner conjecture, which is mathematically not proven. But here I have a numerical thing that it actually, but numerical proof is not. In mathematics, nothing is obvious. That's my undergraduate professor says, you have to prove it. There's nothing obvious in mathematics. And it took Newton to 65 pages to prove 1 + 1 = 2 in Principia. So nothing is obvious in mathematics. That's too much. That's the first thing my math teacher told me in undergrad. This is not a proof, but this is strong evidence or circumstantial evidence, whatever you want to call it. But it's interesting. That means if I take a manifold with infinite many and I try to deform it, basically it doesn't matter, whether I have 200 holes or 300 holes, almost, it's asymptotic. Was there another question, one more question somewhere? Okay.
Thanks, Avadh.
Thank you.